Hello and welcome back to the Learn Along series. We're currently doing NLP with deep learning. I believe this is stream number 19. I'm beginning to lose count. But today there's another working session where we'll try to basically attempt one of the assignments. I think yesterday we did assignment 3. Today we'll try to do assignment number 4. Uh, I'll make sure I have everything downloaded so that we can jump right in. Give me 1 second. I think assignment number 4 is for uh, neural machine translation with RNNs. So we've already covered the lecture for this a while ago. So let's try to see how far we can get. Plus, I think we can also review uh, probably the solutions and also just go through those to make sure uh, you're getting an idea of what it is. Okay, so I think I have this downloaded, but we might need to create a Jupyter notebook just like we did for the last ones. I'm just looking into what all material is there. Let me switch to learning mode. Okay. I'll also quickly check the sound. Okay. Yeah, I believe I need to copy one of those notebooks. I'll take this on the other screen. I don't know why, but for some reason my Google never really got fixed. Google Drive syncing. Give me 1 second. Okay, sorry for the wait. Uh, so I'm just basically going back to assignment 3 and copying our Jupyter notebook. For some reason, I was saying my Google Chrome has still not fixed itself. It's still not syncing. I don't know what. I might have to need to restart my laptop sometime later. But oh, make a copy. Okay, so I'll just rename this just for the sake of optics. I don't know why everything is so slow. But hopefully stream is not lagging. I mean, it says excellent connection, so I think we're fine. Okay, let's jump right in. Assignment 4. The assignment is split into two sections: NMT, analyzing NMT systems. The first is primarily coding and implementation focused, where the second is entirely consists of written analysis questions. So, okay, you get stuck on the first one, you can always work on the second. That being said, NLP system is more complicated than neural networks we have previously constructed, and takes 4 hours to train on GPU. Thus, we strongly recommend you get started early. Okay, so we'll try to get to the point where we need to do is just like train the final one, and then what I'll try to attempt to do is train this later on and let you know if there's any issues or any new things, any new discoveries. But yeah, let's get started. In 1 second. Okay, in machine translation, our goal is to convert a sentence from source language to target language. In this assignment, we will implement seek-to-seek network with attention. Nice. To build an NT system in this section, describe the training procedure for the proposed NT system, which uses a bidirectional LSTM and unidirectional LSTM decoder. Okay. Given a sentence, we look up the word embeddings from an embeddings matrix, where M is the length of source sentence and E is the embedding size. We feed these embeddings to the bidirectional encoder, yielding hidden states and cell states. Yep, forward and backward version are concatenated. We then initialize the decoder with the first written state, linear projection of the encoder's final state and the final cell state. But isn't that taking a... There's no attention? Oh yeah, okay, yeah. We then use this to compute multiplicative attention. Okay. This is the attention score. We now concatenate the attention output with decoder. Passes through linear layer 10H, dropout. Okay. Follow the instructions on the CS224 and a 0 guide link also provided in the website and Piazza in order to create your VM instance. This should take you 45 minutes. Now, do we have access or is this just internal students? Azure subscription for the class. Never mind, we'll try to build this on Colab. Let's look at the YML file. I just woke up like 5 minutes ago, which is why my hair is how they are. Didn't really get time to shower. Okay. Where is the YML file? In this. Oh, okay. Let me open this offline. Local environment, PyTorch. I mean, I think we already have all of these. What is doc opt? Let's try to just run the Colab file to see. We don't need this. We didn't need this last time as well. I'll just try to import. Okay, so we have that too. And what about torch vision? Okay, so I believe we have everything. I will try to run the TPU, close other sessions. Alright, so we don't need this step. In order to apply tensor operations, we must ensure that the sentences given in the batch are the same length. Thus, we must identify the longest sentence in a batch and pad others to be the same length. Implement pad set function in utils py. Go to utils py. So here it is. Okay. I'll take myself off so that you can see. Sorry about that. So uh, we have to create padding for each sentence. Okay. Now I believe we already had this running. Let's see if we have answers on this website. I don't see anything for padding. This is to initialize the encoder. Okay, here it is. So max sentence length is max length for s in cents, and then for cent in cents, cents varied dot append the max sentence minus the whatever the length of the sentence is. Okay. The way to test is the padded sentence. I mean, there's no output, right? Or do I need to mount this first? Yeah, I'll do that quickly. I don't know why this happens every time, but maybe a good thing. Okay. Success. We don't want to go to this cell. We actually want to go to A4. Or do I need to now go back? How does this work? No. Yeah, I think we're already in there. Oh yeah, okay. Now I wanted to try to see if can return sentence padded. Or test this one, but I don't know if there's a test built in anywhere. I was just trying to restart Google Drive so that syncing works, so I don't have to continuously go back and forth in copying and pasting this file. But essentially, I don't see any way to test this particular code, so we'll just keep moving to the next one. Uh, Implement the unit function in the model to initialize the necessary source and target embeddings. Okay, let's try to understand the model embeddings code, which is here, and zoom in. Yep, here. My system's crashing, I don't know what's happening. Page unresponsive. Fantastic. Okay, now everything has happened at once. God, it's crashing again. Just reload the page. Give me 1 second. Until then, we'll see what we have to initialize. So this is the model embeddings py import torch. So this is the class that converts improvers into embeddings. Self, embed size, vocab. So we assign default values. We define IDs. Code your toLine. Initialize the following variables: self source, self target. Vocab object contains 2 vocabularies. You can get the length of vocabulary by this. Remember to include the padding token for the specific vocabulary when creating. Okay. Hopefully this has reloaded. This is not. Great. No, this is not my internet. Yeah, I'll get back when this gets fixed. How about that? Okay, that took a lot longer than I expected, but I think it's all working now. Sorry for the delay. I think we can just blaze through these now. So we did the util. Let's do model embeddings. I think we already have this open. And here as well. So these are default values, token IDs. So basically all we need to do is just initialize. Then implement the init function in the NMT model file, which is right here. We go back, we find we class NMT, right? The decode is class NMT. No NMT here. Oh yeah, right here. So self-encoded none. All of these default values. Now we have to give these all values. Also in encode. Is that it? Init function, initialize, embedding and layers. Also the encode function here. And then here is the encode. Yeah. So apply the encoder to source sentences to obtain uncoded hidden states. Yep. Additionally, take the final states of the encoder and project them in order to obtain initial states for the decoder. This is the tensor X of source sentences with shape, blah blah blah. Note that there is no hidden initial hidden state of cell decoder, compute by applying encoder to X. So output HC self encoder, back padded sequence X and source lengths. Concatenate the forwards and backward distances to obtain intensity shape B 2H. This is H0 decoder in the PDF. B is the batch size like this. Okay. Similarly for C. Okay. Did that. We did that. You can run a non-comprehensive execution. Yes. So that's what we want to do. Make sure. I don't think we need to import anything. Okay. The next step is to implement the decode function in the same file. We did encode, okay, decode. Decode initializer must not create a matching sequence. Okay. Yeah. I'll go to the code. So to the hidden projection, self attention projection, go to hidden. By self dot model embeddings target padded. Apply the attention to encode hiddens to obtain projected. Yeah. Shape B, source length H. B is batch size, source length. Is applying to H. Okay. It's described in the PDF. Okay, I don't see it, but let's see. Construct tensor Y of target sentence with shape using the target model embedding. Okay, this is what that is. Use the dot.split function to rid of the time dimension Y. Okay. Squeeze YT into a tensor dimension PE. Or just dot squeeze. Okay. Y bar T by concatenating YT O pre on the last dimension. But why are we doing this? Use the step function to compute the decoder next cell state, as well as the new combined output OT. Append OT to combine outputs. Update OP with a new. Okay. So the encoding for loop. Combine outputs is dot stack combine outputs. Oh yeah, okay. Convert from a list length to single tensor shape. Okay. Where length, target length is maximum target sentence length, batch size, hidden size. When using squeeze function, make sure to specify the dimension you want to squeeze. Did on that? So the YT, okay. Otherwise, you'll remove the batch dimension accidentally if batch size is 1. Yeah, I may need to read through these later, but let's keep going for now. Anything else? Okay, we have to define steps. Before that, let's run this sanity check. Okay, that worked. Implement the step function. This function applies the decoder's LSTM step cell for single time step. Compute the encoding of the target, the attention score, attention distribution, and output. Final combined output. You can run a non-comprehensive sanity check. Okay. A lot of steps here, so let's try to see one by one. Compute one forward step for LSTM decoder, including the attention computation. FRT, decode state, decode hidden state, projected masks, decode state, combine output, attention score. You will not use this outside of the function. Oh, okay. Combine output none. So this is what is initialized. Your code here 3 lines. Apply the decoder to YRT and decode state to open new. Split the decode state into 2 parts. Compute the attention score ET, tensor shape. Okay, aren't we doing a distribution here? But let's see. Yeah, here's the step. None. So both state decoder YRTD. Okay. Dot squeeze dot BMM. Batch matrix to matrix product. Okay. So copy this. Batch matrix to matrix product of all projected to unqueezed HT deck 2. And I actually should have looked into input matrix. Okay, input matrix 2, and then what is star for? First batch, second batch, the first batch, second batch. What is 2 do here? Okay, not really specified. Set t to negative infinity, and encoding mass is 1. Encoding mass is not none. Mask fill, negative flow infinity. Apply softmax to yield alpha t. Use patched matrix multiplication between alpha t and encoding hindrance to obtain the attention output AT. Alpha t is shape P source length. Encoding hindrance is the shape. You will need to do some squeezing and unsqueezing. Okay. Concatenate hidden to compute UT. Apply the combine of UT to VT. Yeah, that's how. By first applying 10H. Okay. So going one by one. Alpha t is functional softmax. Okay. Just copy the entire thing first. Uh, Alpha t applying softmax function. P source length minus this. AT is torch dot squeeze. Torch matrix multiplication unsqueezed. Alpha t 1. Okay. Torch concatenate this. Self combine. Self drop out. Save. Let's try to run this sanity check. And then function times is deprecated. Use torch.nh instead. Let's do that. Should be fine. Didn't it get uploaded? No. That. Okay. Execute the following to generate the necessary vocab file. Can we do this here? Oh, my bad. This take a lot of time. We already have. Let's see. Now, as noted earlier, we recommend you develop the code on your personal computer. Confirm that you're running on the content environment and execute the following command. You train the model on your local machine. Once you've ensured that your code does not crash, power on a VM. Yep, we don't need this. Finally, turn to a managing process on a VM section. Practical guide. So we need to do this next. Wait, where did it download? I think it created this JSON file. Try to do the local training. This works. What is the GPU requirement txt? Once your VM is configured, you're in a TMX session. Execute this. I think this is the next step. Then test. I'm not sure how long will this take. I mean, local files should take lesser time used by CPU. It's using my CPU. Is it? I mean, why was there a local step in the first place? We recommend that you develop the code on your personal computer. Confirm that you are running in the proper content environment. Then execute the following command to train the model on your local machine. Once you've ensured that your code does not crash, oh, let it run till iter 10 or iter 20. It ran till iter 20. Yeah, I think it should be fine. It didn't crash. Then, okay, fair. So I think we can stop here. I'll basically now run train and test and see what the score comes in. But for the code part, I think the real homework is now to just read through all of these codes. I'll just stop this. Yep. And get rid of this cell. Yeah. So basically, just get to know what exactly happens on each step, because it's one thing to just have the code running, which we sort of uh, took from to most of the help from this, but more importantly, I think it's more about the concept of why it's happening, what it's happening, and it's beginning to tweak stuff a little bit. So yeah, I think that is it about this assignment. I'll check what the blue score comes out to be. In class, we learned about dot product attention, multiplicative attention. Yeah, we'll try this once this runs. Please provide one possible advantage and disadvantage. Basically, just changing these three attentions. I know it'll take a whole lot of time, so it's more of a background activity for me throughout, let's say, a day or two. I think the others were just these are, I think, just theoretical questions. So we are okay there. Okay. Um, Second is entirely consists of written analysis questions. Maybe we can use these prompts on question 2 to test our model, but more or less the idea is let's okay, no, never mind. I think that's it for today. A little inch by inch closer to understanding what happens in the background, but more importantly, being a little more hands-on and getting comfortable with the code. Now my objective is to just have this code in front of me every time I'm trying to do something, and then use this as a reference to gain more and more understanding. So I have, one from beginning to the end, uh, a ready to go code that also explains step by step what we had to do in order to build that particular piece of code. Uh, yeah, so I think that's it for today. I'll see you guys tomorrow. We probably would be reviewing the other, uh, the previous uh, lectures. I think lectures 9 through 12 to another review session. But let's see. I may have another working session if I find anything else that may help us, improve upon all that we've done so far. Just looking through the course web page. or maybe just look at, you know, uh, I don't know, like a PyTorch tutorial. I think that I had one of that in mind to basically start doing stuff more on PyTorch from like people who, there's people like, as I was saying, Sentex and other YouTube creators who just code, and you can just basically live code with them. Uh, but I keep keep an eye, subscribe to my channel, hit the notification bell. You'll see I always try to schedule my streams. I think I've always done that so far. Uh, Same time as always. Until then, take care, and I'll see you guys in the next one.